All right, so we're in section 9.7. So what we're going to take a little bit of a detour from infinite series today.
Taylor polynomials.
Talk about Taylor polynomials, and then we'll bring it back. We'll kind of bring infinite series back into our discussion next time. So our idea here is we want to develop a procedure for approximating functions. So we want to approximate functions with polynomials. Before we start talking about our procedure, why do you think, why would we want to do this? Why would we want to approximate functions with polynomials? Take an easier derivative or an integral. So that's one reason. And also, there are times when it makes it possible to approximate an integral. So, for example, if we were looking at e to the x squared dx, we can prove that this integral exists, that this indefinite integral exists, that there is. We can prove that there is an antiderivative, but this antiderivative cannot be expressed in terms of elementary functions. So we can prove that it exists, but we don't necessarily have a procedure for writing it down. And Taylor polynomials gives us a way, or can give us a way to approximate this. So that's one reason. Anybody think of another reason why we would approximate functions with polynomials? Chris?
Relating them to infinite series and manipulating them as an infinite series to find that they converge or diverge, something like that.
Okay, so we want to relate these functions to an infinite series and use the tools that we've talked about for infinite series to talk about these functions. That's another reason. And it wasn't necessarily originally developed for this purpose, but I guess kind of along the lines. Well, what any of you work with or into computer stuff, working with computers? So what operations are computers good at doing? Addition. Not even subtraction, right? They're not as good at subtraction. And multiplication is just repeated addition, right?
And
so polynomials allow us to express functions in terms of, essentially in terms of multiplication. So on our calculators, when you press the natural log button to find the natural log of a number, you press the cosine button or the sine button. Your calculator is some kind of algorithm that doesn't have a big table of those stored in there. It's doing some kind of approximation of those functions. It might not necessarily be a Taylor polynomial, but some kind of approximation for those functions. So computers don't know how to take natural logs. Computers don't know how to find the sine or the cosine of a number. You have to give it an algorithm, and polynomial approximations is one way to have algorithms for calculating these things. So that's just a little bit of our motivation. All right. So for Taylor polynomials, just so we know our notation might be different than what you've used before. What we're going to call our polynomial, our book calls them p of x. And we're going to expand, we're going to pick a point in our domain of our function to expand our approximation about. So we're going to pick a point C. We call our point C that we expand about, or we make our approximation near that point. So we pick a point C in the domain, and we're going to say that we expand about c, or we're going to say that our polynomial is centered at c. And the kind of a nice idea that I heard explained by a teacher talking about these polynomial expansions is kind of like we saw a car moving by, driving outside. We saw this car outside of our window, and we leave the room. But when we come back, we want to have an idea of where the car is. We can start by knowing where the car was when we left. So we can start at a particular point. Then if we want to have a better idea of where it might be at some time in the future, we can look at its velocity, and that might help us to approximate where it is. And then we could look at its acceleration from that point forward. And so all of these things are helping approximate where that car might be at some point in the future after we saw it at one initial point. So that's kind of what we're doing, in that the point that we saw it is kind of like our point C in our domain. We have to pick a point where we're starting, and that's where we're making our approximation. So we're going to expand about C, or we're saying our polynomial is centered about C, and we have some requirements. And so we're approximating our function f. And our requirements are, we have some requirements. We want the function and the polynomial to agree at this point. So we want our requirements for this approximation is that f of c equals our polynomial at c. And like I said in our in kind of our explanation of what we're doing, so we want our function to agree. We also want our first derivative to agree. So that's our second requirement for our polynomial. So f prime of c has to equal p prime at c. And we continue this process to make our approximation more accurate, and we want our second derivative to agree. And we continue this to our desired accuracy. So we want the function to agree at this particular point, and we want all the derivatives to agree at that particular point. So let's write an expression for our polynomial and see what these requirements make, what kind of form that gives our polynomial. So we're going to write that our polynomial, and this is for n terms, piece of n of x is, and we're just writing an expression for our polynomial. So this is our nth polynomial. We have our highest power here is n. So this is our nth polynomial. And we're going to determine our a1, a2, a0, etc. So we're going to determine these based on our requirements. So now we're going to write an expression for all of our derivatives of this polynomial that we haven't figured out what its form is yet. We're going to write an expression for the derivatives, and then we're going to use our requirement that the derivatives agree with the function at c. So if I take the first derivative, p prime, take the first derivative, I get a1 plus 2a2 x minus c plus, and I'm going to write my third term, 3a3 x minus c squared plus dot dot dot, and I have n times a sub n x minus c to the n minus 1. So I just took one derivative here. And I'm going to take another derivative, take the second derivative, p double prime, of this polynomial. And we're going to write what that is. We get 2a2 plus 2 times 3a3 x minus c plus dot dot dot, and then we get plus n times n minus 1 times a sub n x minus c to the n minus 2. And we continue taking derivatives of our polynomial until we've taken n derivatives. So I'm going to go down here and I'm going to say that our nth derivative, and the way we show higher derivatives is we put our, instead of prime, double prime, we're going to put our n in parentheses. So this means we've taken n derivatives. So our nth term, everything's going to, all of these terms are going to go away because we've taken derivatives. We end up taking derivatives of constants. And all we're going to be left with after we take n derivatives is n times n minus 1 times n minus 2 times dot 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 times 2 times 1 times a sub n. And our requirements on our polynomial had to do with when x equals c. So our derivatives and our function had to agree. Our derivatives of our polynomial had to agree when x equals c. That was our requirement. So when x equals c, we have that the nth derivative of c, I'm sorry, not the nth derivative, just piece of n of c, our function at c is just a sub 0. Our first derivative at c is just 2 a sub 2. Oh yes, sorry. One derivative ahead, aren't I? A sub 1. Our second derivative. That's where I got one derivative ahead there. Second derivative is 2a sub 2. And finally, our nth derivative at c is just n factorial times a sub n. And these have to agree with our function and our function's derivative and the function's second derivative at x equals c. So when we make those requirements, that tells us that f of c, our function at c had to agree with our polynomial at c. So f of c has to equal a0. F prime of c has to equal a1. And I'm going to simplify a little bit. F double prime at c divided by 2 factorial equals a2, because I'm getting rid of this factor of 2 here. And finally, my nth derivative at c divided by n factorial has to equal a sub n. So we've equated our polynomial, our derivatives, and our n derivatives, and solved for our a's, a0, a1, a2, etc. So this gives us a process for finding these a values depending on our function. So using this process, we're going to use this to define our nth Taylor polynomial and our nth Maclaurin polynomial. So Our process is to equate the function and the polynomial at the point we're interested in and equate all of their derivatives. And that gives us this process for finding these coefficients of our polynomial. We're going to use this process to define our Taylor polynomial. Everybody follow the process. Okay. So our nth Taylor polynomial and we're also going to say the nth Maclaurin polynomial. Oh, that's a Maclaurin. So we're going to use that process to make our definition. So we're going to say that f has n derivatives at c. At some point c. P sub n of x equals f of c plus f prime of c times x minus c plus, and we're just writing our coefficients now in terms of our derivatives. And we go out in terms, or after we've taken n derivatives. I'll write it this way. So this is the nth Taylor polynomial for f at c. So this gives us a process, a procedure for writing, for approximating a function, a particular function, as long as we have n derivatives, for approximating this function at some point in its domain C. And we give it a special name if c equals 0. So we're expanding about 0. That simplifies our expression. Then we call our polynomial the Maclaurin polynomial. The Maclaurin polynomial is just the Taylor polynomial expanded about 0. So this is our nth Maclaurin polynomial. So now we have a process, we have a procedure where we can approximate these functions. We can figure out as many terms as we want to, or as many terms as we're willing to calculate, so we can approximate functions with polynomials. This gives us a procedure for doing that. So questions on the procedure. And the reason that this takes the form, just to backtrack, to re-emphasize what we've done, the reason this takes this form is this polynomial now satisfies the requirement that our functions agree at our point of interest at c, our first derivatives agree at c, our second derivatives agree at c, etc., for as many terms as we want to take. All right, so let's look at an example, couple of examples of finding Taylor polynomials of a function. So the nice part of Taylor polynomials is they give us this nice polynomial expression for a function. The downside of Taylor polynomials is that calculating the coefficients sometimes can get tedious because we have to take a lot of derivatives. We have to do a lot of calculation. But let's look at a couple of examples. So we want to find the first four Taylor polynomials so I'm looking for P0, P1, P2, and P3. For my function, we'll do an easy one, 1 over x, centered at c equals 2. So the way I usually do these, just the little kind of format that I usually use for finding these coefficients is first I just make a column for my function, and then I do my derivative. So I'm going to have to get my four Taylor polynomials, P0 through P3, I need 3 derivatives. So f prime is going to be what?
Negative 1 over x.
Minus 1 over x squared. F double prime,
1 over x cubed.
1 over x cubed. And my third derivative,
2 over x. Oh, yeah.
we get 2.
Yeah.
And my third derivative,
Negative 6
-6
over x.
over x to the 4th. And then we're going to calculate these at c equals 2. So f of 2, I like to make them in columns. That just helps me to keep them straight. So f of 2, and I'm going to leave them as fractions. F of 2 is 1/2. F prime of 2 is negative 1/4. F double prime at 2 is going to be 2/8 or positive 1/4. And my third derivative at 2, I get minus 6 over 16 or minus 3/8. So now I can write I have my coefficients now for my polynomial. So P0 is going to be my first approximation. My first approximation is just going to be 1/2. So that's my first Taylor polynomial for this expanded at around c equals 2. My P1 is going to be 1/2 minus 1/4 times x minus 2. P2, I'm increasing my accuracy with each term. When I substitute my coefficients in, I get 1/2 minus 1/4 x minus 2. And I'm going to write this unsimplified first, plus 1/4 times 1 over 2 factorial times x minus 2 squared. And then my P3, I'm just adding another term here. So I get 1/2 minus 1/4 x minus 2. Get all the terms I had before, and I'm just going to add one more term. Plus, when I simplify this, I'll write the simplified version of this, 1/8 x minus 2 squared. And my last term is going to be, I'm going to just write the simplified version, minus 1 over 16 x minus 2 to the third. So those are my first four Taylor polynomials for x expanded about c equals 2. So for x values near x equals 2, this is going to be a very good approximation. If we wanted to approximate, for example, if we wanted to approximate 1 over 2.8, we could, since 2.8 is relatively close to 2, we could use this Taylor polynomial and get an approximation of 2.8. What's another way we could approximate 1 over 2.8? Centered around 2.8, or if we wanted to, that we definitely could do that. What would be just something close to 2.8 that would be a little easier to work with? We could expand about 3.
Plug into your calculator.
You could plug it into your calculator. Let the calculator do it.
Or just do 1 over 2.8.
1 over 2.8. What I'm going to say is, since 2.8 is closer to 3, let's expand 1 over x plus 3. 2.8 is close to 3. So let's expand 1 over x plus 3 about c equals 0. So that simplifies our terms a little bit, so we don't have the x minus some factor. So we're going to, my suggestion is let's expand this about c equals 0. And then this will give us an approximation close to 1 over 2.8. So let's do this expansion. So my function is 1 over x plus 3. My derivative is minus 1 over x plus 3 squared. Second derivative is 2 over x plus 3 to the third, and my third derivative is minus 6 over x plus 3 to the fourth. And just as a kind of a general suggestion, if you can expand about c equals 0, that usually makes your life a little easier. The expansion is usually a little easier.
Why is there 1 over x plus 3?
Yeah, 1/3 is close to 2.8.
But couldn't you just do 1 over x about c equals 3?
You could do 1 over x about c equals 3. You could do that as well.
Just different ways of writing it.
Yeah, just different ways of writing it. And basically what I'm doing, I just want to do this different expansion, and then we're just going to compare the results, just to see how different our two different expansions, how different our approximations are. That's my point in doing this. We could do any other expansion. I just want to compare the results. So f of 0 is 1/3. F prime of 0 is minus 1/9. F double prime of 0 is 2 over 27. And F triple prime at 0 is minus 6/81st, or minus 2 over 27. And I'm just going to write, rather than write each term, I'm going to write the fourth polynomial. I'm just going to go ahead and write out the expression for P3. So my P3 of x is 1/3 minus 1/9 x plus 1/27 x to the third, x squared, minus 1/81 x to the third. So this is my approximation, expanding 1 over x plus 3 about c equals 0.
Oh,
Yeah, I simplified all the terms altogether, so I didn't write out all the intermediate steps. So let's compare our approximations. In our original series, when we expanded 1 over x, here, centered at c equals 2, if we calculate this approximation for x equals 2.8, I'm going to say that this is approximately, in our original series, we end up with about 0.3480 using this approximation. And if we expand 1 over x plus 3 about c equals 0, I get that in order to do this, I'm going to let x equal negative 0.2. So when negative 0.2 plus 3 is 2.8. So I'm going to plug in negative 0.2 into this, and I get that this is negative 0.2 plus 3 is approximately, with this approximation, 0.3571. And if you plug that into your calculator, what does your calculator give you? 1 over 2.8. Anybody have one handy? 1 over 2.8 in your calculator? 5714.
Yeah.
So our second approximation, our second series, is a little closer to what the calculator tells us that it is, because we expanded about our approximation was closer to our original value. And if we would have done what Mehmed said and expand, what was your suggestion? Expand about 1 over x about x equals 2.8, then we would have an even better approximation. Our calculations would have been a little more difficult, but we would have gotten a better approximation. So questions on finding Taylor polynomials. Finding them, I think, is not really knowing where they come from is good, and being able to get them is good. Finding them is not necessarily the interesting part. We're going to get to the interesting part in the next lesson, when we actually start using Taylor polynomials. When we have some Taylor polynomials, and what can we do with them? That's when it starts getting interesting, in my opinion. All right. Homework. There you go.